Section 7-3 is on other differential equations. The objective of this section is to write and solve a differential equation and use the solution as a mathematical model to make predictions. And as you saw in the first half of this section, the types of differential equations that you're working with are not the same that you saw in the last section. So it's extremely important that you're able to read the question there and understand the differential equation they're describing to you, be able to write down that differential equation, be able to separate the variables, and then solve that differential equation using integration. Plugging in your initial condition will get you your particular solution, and then you can answer some questions about it. All right, we got a lengthy example to go through here, so let's get started. This dam leakage problem. Example number 2. It says a new dam is constructed across Scorpion Gulch. The engineers need to predict the volume of water in the lake formed by the dam as a function of time. At time t equals 0 days, the water starts flowing in at a fixed rate F, which is in cubic feet per hour. Unfortunately, as the water level rises, some leaks out. The leakage rate L, which is also in cubic feet per hour, is directly proportional to the volume of water, W, which is in cubic feet present in the lake. Thus, the instantaneous rate of change of W is equal to F minus L. All right, so part A says what does the L equal in terms of W, and write a differential equation that expresses dw dt in terms of F, W, and T. Well, first let's write down all the variables and constants they've described here for us so we understand those. And let's start out with our variables here. So the first one was W, which W they told us in the second to last sentence is the volume of water. And that was measured in cubic feet. So W is our water, or volume of water, however you want to write that. And then our independent variable here is going to be time. So we'll use T for time. And we are measuring that based on the rates they gave us in hours. And then finally, there's two other values, two other rates they actually specified here. One is, the first one they mentioned is F, which is your flow rate, the rate at which water is flowing in. This is your flow rate. And that was measured in cubic feet per hour. And not only that, they tell you it's a fixed rate, so that means it's a constant actually. I'm just going to put that. So this is a constant. Okay, water is flowing in down this stream or whatever that's filling behind the dam there, so it's flowing in at a constant rate. And the last one they tell you is this leakage rate L. And that's also measured in cubic feet per hour. That's not a constant. Depends on how much water is behind the dam. The more you have there, the higher the pressure, thus the faster that you are going to lose water through this leakage rate. All right, so again, part A says, what does L equal in terms of W? So this is the second to last sentence they tell you there. It says the leakage rate L is directly proportional to the volume of water W. So L, they tell you, is directly proportional. That means it's equal to some constant times the volume of water, which is W for us. So L is equal to K times W. And then they also say to write a differential equation that expresses dw dt in terms of F, W, and T. All right, so that last sentence of this problem tells you that relationship that we need. It says, the very last sentence, thus the instantaneous rate of change of W, that's dw dt, is equal to F minus L, which should make sense to us that F is how much water is coming in, or I should say it's the rate at which water is coming in, and L is the rate at which you're losing water. So the difference of those tells you overall the rate at which the volume of water is changing, dw dt. And they wanted this in terms of just F, W, and T, so I need to get rid of L, but they told us what L is equal to. They said that L is equal to K times W, so this is F minus K times W is our differential equation there. All right. Let's take a look at part B now. Part B is where the work is going to take place here for this problem. Part B says to solve for W in terms of T using the initial condition that when time is 0, W is equal to 0. So there's no water behind the dam initially. All right, solve for W in terms of T. So our method that we have to solve a differential equation, the only method you have to solve these algebraically is the separation of variables method. That's the only method we're going to talk about. So to do that, I have to get all of the W's on one side and all of the T's on the other side. Those are my two variables here. So in other words, I've got to take whatever's in the denominator here, the dt, and I got to move him to this side. And then anything that has a W in it, which actually the whole thing does, I got to move the whole thing over to this side. All right, I can only move stuff through multiplication and division. I can't add or subtract to do what I need. I need to be multiplying by my differential, so I have to use multiplication or division to do this. So we're going to end up with dw divided by f minus kw, and that's going to be equal to just dt. All right, so that's the first step, is our separation of variables. Now the next step, once we have our variables separated, is to actually integrate this thing. So we can integrate dw divided by f minus kw, and that's equal to the integral of dt. All right, now the right side is the easy part. The left side is a little bit tricky, but it's really just dw divided by some linear function. So that looks a lot like our reciprocal function. And in fact, doing a u substitution on this might help if we let u be the denominator. U is equal to f minus kw, and take the derivative of that. Now when you do this, remember that w is the variable here. F and k are constants. So derivative of f is 0 then. Derivative of negative k times w is going to be negative k times the derivative of w, which is 1. And then we multiply that by dw. And the only thing I don't want to have is that negative k there. I can see I have a dw in the numerator, so let's divide by the negative k to find out dw is actually equal to a negative 1 over k du. And we'll go ahead and use that substitution here just to make this antiderivative a little bit easier. So we end up with dw is negative 1 over k du in the numerator, and that's over u in the denominator. We could integrate this right side, but I'm going to go ahead and just leave it like this until we integrate the left side. Let me factor out the negative 1 over k from the left side, or on the left side, and rewrite this as du over u. And hopefully in that form it helps you recognize that's our reciprocal function we're integrating. That's what we learned in chapter 6. The antiderivative of that is our natural log function. So this is a negative 1 over k times the natural log of the absolute value of u, and that's equal to the antiderivative of dt. There's really a 1 dt there, so the antiderivative of a constant is just the constant times your variable, so it's 1 times t, or I'll just write that as t. And we've been adding just the constant of integration, the plus c, to one side of this equation, and so we'll put it over there with the right side. All right. Next step of this is to replace u with what it's equal to. We have a negative 1 over k times the natural log of the absolute value of f minus kw. That's equal to t plus c. Now again, don't lose sight of what we're trying to do. We're trying to solve for w, the amount of water, as a function of time t. So I've got to move this negative 1 over k to the other side, so we'll multiply both sides by a negative k. So we have the natural log of the absolute value of f minus kw on the left side is equal to a negative k times t, and then it's a minus k times c for the second term. All right, again, we're trying to solve for w, so I got to get rid of the log, so exponentiate both sides to base e. Or you can think of this as using your definition of logs is another way to think about how you're solving this thing. Both of those will give you the same result, of course. Over here on the left-hand side, of course, e to the natural log, those are inverses of each other, so they cancel each other out in essence. So you end up with just the absolute value of f minus kw on the left side. And I'm going to rewrite what we have over on the right side. We usually rewrite that as e to the negative kt times e to the negative kc. And that e to the negative kc is some constant here that we're going to rewrite in just a second. I'm going to get rid of our absolute value, the same method that we've used before. Just rewrite that as plus or minus some value. It's not both, it's one or the other. That's what absolute value does. It gives you a positive value every single time. So if your value was negative, you take the opposite of it to make it positive. If it was already positive, then you leave that alone. And I'm going to put the constant, the e to the negative kc, out front times e to the negative kt. And this guy right here is just some constant. And so I'm going to rename him. I'm going to say that we're going to let C1 be equal to the plus or minus e to the negative kc. Now again, you don't have to name that every time, but if it helps you in your work to be able to go back and look at it, certainly do so. So we end up with F minus kW is equal to C1 times e to the negative kt. And we're almost there. We got to get rid of the F and the K from the left-hand side. So let's subtract the F. So we have a negative kW is equal to a negative F plus C1 times e to the negative kt. And last step is to divide by negative k. Look at that. W is equal to, I'll just distribute this as I go. So negative F over negative k is F over k. And then it's going to be minus C1 over k times e to the negative kt. All right, we did it. There's our solution that we're looking for. They said to use the initial condition, though, so we're still not quite done here. It says using the initial condition that when time is 0, W equals 0 to help us solve this for C1. So T equals 0, W equals 0 is the initial condition. So let's plug those in. So we'd have 0 is equal to F divided by K minus C1 divided by K times e to the negative k times 0. Oh, that's nice that they let us plug in 0 there. E to the 0 there is going to be 1. So you're going to end up with C1 over K, when I move it over to the left-hand side, is equal to F over K. Again, the e to the k times 0 is 1. So I can slide that over the other side, add it to the other side. If I multiply through by the k's there to cancel those out, I'll get C1 is equal to F. So F is equal to C1 there for us. So let's plug that into our equation then. The equation we end up with, I'll write it as a function, or in a function notation here, W as a function of t is equal to F divided by K minus F divided by K. Again, we are replacing C1 there with F times e to the negative k times t. In fact, since those both have coefficients of F over K, it might be easier just to factor that out front and write that as 1 minus e to the negative kt. You can leave it in either form. There's fine. There is our function, W as a function of t. All right, part C, it says the engineers know that the flow rate F is equal to 5,000 cubic feet of water. So for part C, they're telling us F is equal to 5,000. And based on geological considerations, the proportionality constant and the leakage rate is assumed to be 0.04 per hour. So that's the K value. K is equal to 0.04. So they gave us those two constants there that we still didn't know. And it says write an equation for W is substituting these quantities. Okay, well that's not too bad then. Just take this equation that we have here and plug in those two numbers there. So we have W of t is equal to, it's going to be the 5,000 divided by the 0.04, that's F divided by K, times 1 minus e to the negative 0.04t. There's our particular solution then for these given flow rates and that constant proportionality. In fact, the 5,000 divided by 0.04, let's go ahead and simplify that. If you take 5,000 divided by 0.04 on your calculator, I'm just going to quickly do that. You get 125,000 times 1 minus e to the negative 0.04t. All right, so there's our equation, W as a function of time. Part D, it says predict the volume of water in the lake after 10, 20, and 30 hours. All right, and it also asks us to, after these intervals, how much water has flowed in and how much has leaked out. All right, so we have a little bit of extra work there to do with those in addition to just simply finding what's happening at 10, 20, and 30 hours. But let's use our calculator to help us out. Again, there was that constant we just calculated. So in y1, let's put in our equation. It's 125,000 times 1 minus e raised to the negative 0.04 times, I got to use x there, of course, in order to graph this, or not graph this thing, but use my table. I'm just going to go to my table and make sure it's set up right. We're going to start it out at 10, since that's the first value they wanted here. And I'll have it changed by 10, because they want 10, 20, and 30. So that will give us a table of the values that we're looking for. So it looks like at 10 hours, we're at 41,000 and some change cubic feet of water. At 20 hours, it's 68,000, a little more than 68,000 cubic feet of water. And at 30 hours, we're almost up to 87. We're a little over 87,000 cubic feet of water. All right. They also said then, after each of these intervals, how much water has flowed in and how much has flowed and how much has leaked out. Well, they told us the flow rate. If we go back here, they told us that F, our flow rate, was 5,000 cubic feet per hour. So it's flowing in at a constant rate. So if I just take the rate and multiply by how much time has passed, I can find out what my how much water has flowed in. So let's punch that into the calculator then. So in y2, we'll take 5,000 times x. And let's just look at the table there just to make sure that those numbers make sense. So after 10 hours, if we're adding 5,000 cubic feet of water per hour, after 10 hours, it would give us 50,000. And after 20 hours, 100,000 cubic feet of water, and so forth. So actually, the 50,000 there after 10 hours tells us how much water has flowed in. The 41,000 in y1 tells us how much water is still there, which means the difference between these two tells us how much is leaked out. So let's actually use that in y3. In y3, we'll tell it to take y2 minus y1. And let's see if that gives us our leakage rate there. And so the first leakage rate should be around 9,000, a little less than 9,000, because it started out with, or we've had 50,000 cubic feet of water flow in. We only have 41,000 and some change remaining, so about 9,000 is all we should have lost, and that's what we're at. Okay, so there is our flow rate and our leakage rate, or our volumes of leakage and volumes of flow. All right, part E says, when will there be 100,000 cubic feet of water in the lake? Well, I guess since we have this table here, we can kind of see that. Let's go back to Y1, which tells us how much water we have in here. So after 40 hours, we're just under that mark. We're at 99,000 and some change cubic feet of water. So we're pretty close. So it's just after 40 hours. In fact, at 50 hours, we can see that we're up to 108,000. So we definitely reached it by then. So somewhere between 40 and 50 hours, I would expect, is where the answer we're looking for. But let's actually solve to find out what that is. I'm going to use the solver to do that. You could graph this and graph the line 100,000 with it and find that solution too. I'm just going to use the solver, though, just for the sake of using it, I guess. Let's go up here and clear out this equation. And let's just tell it that we're going to take y1. And remember that to use solver, you have to have this set equal to 0. So the equation that we're solving, I guess I should write that down here first for us before we go too far. This is for part E. They're asking us when our amount of water will be equal to the 100,000. But again, I can't solve an equation like that in solver. I have to have it set equal to 0. So I got to subtract the 100,000 is what I'm going to do. Y1 minus 100,000. All right. And I'm not sure exactly where it occurs, but I'll put in a guess here of 40. I know it's somewhere around 40. And then press alpha and then enter. We'll solve this thing. There we go. 40.236. 40.236. T is equal to 40.236 hours. So just over 40 hours later, we've got 100,000 cubic feet of water, less than 2 days. All right, part F says, find the limit of W as t approaches infinity and state the real-world meaning of this number. Okay, so we'll do a little limit problem here with this. So for part F, we want to find the limit as t goes to infinity of our equation for W, which is the 125,000 times 1 minus e to the negative 0.04 t. All right, so if we let t go to infinity, there's only one t in here, and so you'd end up with e raised to the negative 0.04 times infinity, which is e to the negative infinity. So realize that this part right here is taking on the form of e to the negative infinity. Now, if you don't recognize what that's approaching, then remember what raising something to a negative power means. That'd be the same as 1 over e to the positive infinity. So that's 1 divided by e to a really, really big number, which turns out to be a big number. So you have 1 divided by infinity here. And so this is heading towards 0. This is 1 over infinity in essence, which goes to 0. So that part of it, though, only that e to the negative 0.04 is going times t is going to 0. So we are left with then 125,000 times 1 minus 0 is what we end up with, again, because that last part goes to 0. So this turns out to be 125,000. That would be in cubic feet. That's cubic feet of water. So what's the real world meaning? Well, we're letting time go on forever. And it turns out that it doesn't matter how much time passes, we're only going to achieve 125,000 cubic feet of water. That's what we call the steady state of this system. Okay. And why does that happen? Well, this happens because of the fact that we've got a water flowing in at 5,000 cubic feet per hour, and we've got water flowing out at another rate. And when those two balance out, when those two are equal to each other, turns out that this thing approaches a steady state. So it must be that our leakage rate finally hits 5,000 cubic feet of water. So that means every drop of water that's coming in is leaving. So we don't have any gain in the amount of water that we have behind the dam. All right, look at G. G says to draw the graph of W versus T, showing the asymptote. So again, this here, when we take the limit of a function as T goes to infinity and we get a constant, that's called a horizontal asymptote. Let's see if we actually see that show up here in our graph. We have that equation in Y1. In fact, I'm going to get rid of, though, these other two equations, or at least shut them off. I don't need those to graph along with it. And let's change our window. Let's go from 0 to, let's go to 150 hours. Should be plenty of time for us to get up to that asymptote or get closer and closer to it. And we'll go from 0 to 125,000 is what we said our maximum is. And we'll set a scale of 25,000. We'll just graph that. And we should see that we quickly approach that asymptote, actually. And it just keeps getting closer and closer and closer to it. All right, so that's example 2. Let's take a look at example 3. Example 3 is going to have us work with the same problem. The lake in example 2 is now filling with water. The actual volume of water at time t equals 10 hours is exactly 40,000 cubic feet of water. The flow rate is still 5,000 cubic feet per hour, as predicted. Use this information to find a more precise value of the leakage constant, K. All right, so let's go back to the equation that we had initially here, or that we solved for, I should say. We had W as a function of t was equal to, it was F divided by K times 1 minus e to the negative kt. And they're giving us a new value for F, and we're trying to find out what the corresponding value for K is. So they told us that the flow rate is, the flow rate is still 5,000, so we know that. W of t is equal to 5,000 divided by K times 1 minus e to the negative kt. And they told us that when time was 10 hours, that we had exactly 40,000 cubic feet of water here. So let's substitute in that point. So we have 40,000 is equal to 5,000 divided by K times 1 minus e to the negative K times 10. And so there we go. We've got an equation with just one unknown there, K, and we should be able to solve to find our value of K. You could use solver to do this, or you could actually graph this thing to get your solution. Graph the 40,000, graph 5,000 divided by x times 1 minus e to the negative 10x. Graph those two and find where their intersection is. I'm just going to take the number that they gave you in the book there, but the answer that they turns out to be is 0.046. All right, you can punch that in your calculator to verify that you get the same result.